So, as first things first, let's actually go back uh, to what we're talking about for the exam in terms of just exam policies. Way back at the start of the class, I distributed the syllabus. We've deviated some from that, but certain things are still the same. In particular, the exam policies. So obviously, hopefully you all know Thursday, this coming Thursday is the exam. The usual time and place in this room. You'll have the full time to work through the exam and provide your solutions. And as I'd mentioned before, and as is listed in the syllabus, it's going to be open book, open notes. You can bring anything you want, anything printed, any kind of handwritten materials. You can even print out old lecture slides. You can take the practice midterm exam with you, all that stuff you could take with you. The only things that are not permitted are personal electronic devices. So things like laptops, cell phones, etc. You can have any type of calculator you like. So, graphing, non-graphing, but really there shouldn't be any need to use a graphing calculator. So if you don't have a graphing calculator, that's fine. In some of the homework problems, you'll notice, especially the last one, it required, either using some kind of script. I think several of you used like Python or MATLAB or some other kind of script to solve some of the problems. Problem number 2, I think it was in particular. But I'm not going to ask you to do anything that hairy, at least not in the context of an exam. So you should be able to get by just with whatever type of calculator you bring with you. But otherwise, yeah, the usual other caveats apply, use good judgment, have academic integrity, that kind of thing. Hopefully we don't have to belabor that. In terms of the number of problems on the exam, I would say it'll be similar, at least in scope, maybe a little bit smaller than what's presented on the practice midterm. So the practice midterm that I distributed to you, it's technically 3 problems, but problem number 3 has 3 parts. So it's kind of like, it depends on how you choose to view that. But really, it should be comparable in size to that. Maybe a little bit smaller. All right, so without further ado, we talked about a lot of things. We talked about equilibrium. We defined the stress tensor. We came up with these differential equations of equilibrium. We defined strain in this more general tensor situation. And then we connected strain and stress through our usual elasticity equations or stress-strain relationships. We imposed these requirements of compatibility on how we define a strain field such that it needs to be related to a continuous displacement field. And we solved a bunch of problems. We did a few problems in elasticity, sometimes using simpler methods, sometimes using more complicated methods like the Airy stress function. And we also looked at other things like what are particular problems of interest? What happens if you put a point load on some kind of half plane? What happens if you have contact between different surfaces? And also, we looked at failure criteria. So the goal of the exam is to really do a little bit of all those different things, but not in such an extreme way. And hopefully you'll see, it's an attempt for you to synthesize your understanding of these concepts in a somewhat practical application and context that I think will hopefully benefit you after you leave this class. So without further ado, let's actually jump into the problems. I think we've kind of belabored this a little bit longer than necessary. So let's jump to problem number 1. If you happen to have some kind of computer or tablet with you, or if you have the practice exam printed out with you, hopefully that might be easier to follow along with than this. I think it's a little crammed for space, but I'll summarize the content of this particular problem. I'll read it out to you. All right, so the question asks, determine whether the following plane strain field defined in a piecewise fashion over the domain X ranging from 0 to 1 and Y ranging from 0 to 2, determine whether this plane strain field satisfies the requirements of compatibility. And then I provide you with the epsilon XX strain field and the epsilon YY strain field, both defined in this funny piecewise fashion. So for all points that lie below the line Y equals 1, the epsilon XX strain field looks like this. CY squared And then same thing, similar definition for epsilon yy, where points below that line look like this, minus cx squared. And then it looks different if you're looking at points above that line, basically. And then all other components of strain are just equal to 0, just to make things a little easier. And I'm just saying that this C constant is just some arbitrary variable. Maybe it has some non-dimensional units associated with it, but really the purpose is not to kind of go through the computations here and look at specific values of strain. It's looking more at the strain field. So really, whatever C is, it doesn't really matter. You just have to know that it's the same in all these different expressions. All right, so justify, does this plane strain field satisfy compatibility, and explain your reasoning. So this is kind of your opportunity to demonstrate your understanding through words, and that counts for a lot. So even if you kind of fumble different areas of the problem, maybe you can explain your reasoning and your understanding in other ways. And at least from a grading point of view, if I see that you're kind of like trying to work through a problem, even if you don't quite get to the actual answer that I'm looking for, if along the way you demonstrate your reasoning, maybe you add little notes explaining, this result doesn't make sense, or maybe you say I should be using this particular application of the compatibility equations. If you explain those things along the way, that will count a lot towards partial credit. So do consider doing that in the exam. Maybe not to an excessive degree. Obviously, you want to be able to solve the problems, but demonstrate your understanding. That's really an important thing that I'm looking for. All right. And then in justifying your answer, I suggest that you might want to try sketching things out. So let's actually try that. And before we actually dive into this problem, I'll kind of ask you, what would be your approach to solving this problem? If you were to be given this was the real exam, what would you do? What's the first thing you would do? Integration, you say. So we could do a couple of things. Yeah, we could, if we're given this strain field, one thing we could do is we could maybe try to integrate it to come up with resulting expressions for the displacement field. Is that kind of more or less what you're suggesting? That's a nice idea, actually. There's a couple other things that we might try, and just to kind of get your perspectives, what other things might we try? It's a good suggestion, though. I like that suggestion. Yeah, we could use the compatibility equations in 2D, which ends up being just really one equation that relates the epsilon xx, epsilon yy, and epsilon xy strains. And we could check that. If really what I'm asking for is, does the strain field satisfy compatibility, but I don't give you what the actual displacement field looks like, and I don't give you really any boundary conditions that you could use to figure out what's the specific displacement field that gave me this strain field, then maybe that's probably the most reasonable approach. Try to use compatibility, verify does it satisfy those conditions. All right, so it turns out we're probably going to have to do a little bit of both of those things. And the reason has to do with this kind of funny thing. And again, I'm throwing a curveball at you. I can afford to do this because it's the practice midterm, but it's nonetheless illustrative. So let's try, I don't know, let's try doing the compatibility equations first, just for the sake of argument, because we already have the strains. We may as well kind of do this first. So how do we do that? How do we do that for this particular problem? First of all, what are the compatibility equations in 2D? Maybe it's in there somewhere. In your notes, that is. Who remembers the compatibility equation? Let's see. It involves epsilon xx, epsilon yy, and epsilon xy. Hopefully this is gonna. Well, we might actually have it here, don't we? Yeah, there we go. Here it is. Just to kind of like give you a sense. This is what it is. It's basically the partial derivative of epsilon xy, second partial derivative, in fact, with respect to both x and y. And the compatibility equation basically says that this term has to be equal to 1/2 the partial derivative of epsilon xx twice with respect to y, plus the partial derivative twice of epsilon yy with respect to x. Okay, now forget that I just showed you the answer here. How would we actually go about implementing this? Remember, it's epsilon xy, it's just 0. So its partial derivatives with respect to x and y are just going to go away. So if we had, let's say, partial epsilon xy, this term is 0, right? And then whatever we have left is just what was just shown. Epsilon xx with respect to y squared, yy with respect to x squared. Okay, so this is nice. We can use this, but what about the fact that the strain field is not constant, or rather the expressions for the strain field depend on which section of the problem we're looking at, whether we're looking at things above y equals 1 or below the line y equals 1. So what would be your approach in this case? How would we apply this in this particular scenario? Look at both cases individually? Yeah. So we could, let's say, take only what's happening below this line y equals 1. So consider, just ignore these kind of bottom expressions, and then just say, well, epsilon xx equals cy squared, epsilon yy equals minus cx squared, and we could plug that in and see what happens. We could say, well, the sum of these two things, their partial derivatives, need to basically cancel out. If I'm saying that this epsilon xy term is always 0, then I'm basically saying that these things, have to go away. So does that happen? Well, what's the second partial derivative of epsilon xx with respect to y twice? 2c. And then what about epsilon yy? Its partial derivative with respect to x? Minus c. So we have plus c, a minus c, and basically those two terms will basically just cancel out. So indeed, that kind of upper portion, or rather lower portion of the domain is satisfying compatibility. Okay, that's good. What about for this last one? So xx with respect to y twice gives us, yeah, and epsilon yy with respect to x twice, plus 6c1. So indeed, we get minus 6cy plus 6cy. Both of those terms cancel. So we've satisfied compatibility, and that's basically what we have here. So just illustrating this situation where the dimensions of this small square region can be divided up into these two halves relative to this line y equals 1. Above this line, we have these expressions. Below, we have these. And indeed, we satisfy the compatibility equations, both of them in both of these subregions. Is that it? Can we say, oh, we're done? It would be too easy, wouldn't it? Oh, well. Well, so in most circumstances, it would be enough. And most of the problems that we've considered up to this point in the class really just assumed that there was no piecewise representation of the strain field in this funky way. It was just saying epsilon xx equals, cy squared, epsilon yy equals minus cx squared. And if that were true over the whole domain of this problem, then we could just stop there and say, okay, well, compatibility satisfied, we're done. The problem is we're representing the strain in this discontinuous way. And this might require that you refresh your memory on how we actually presented this concept of compatibility, way back, a couple of weeks ago. Remember what compatibility was. And this is where, if you were working through the problem and if you were kind of explaining your reasoning and writing out compatibility means this, if you said that in words, then, I would definitely give you some points for that. So what is compatibility? Remember, we talked about it. How did we define compatibility? Say again? Yes, the displacement field has to be continuous. That's a requirement for compatibility. If the body is originally an interconnected domain with material points that are kind of connected to each other before the whole thing starts deforming, then after this body deforms, assuming that no fracture happens, there's no like splitting apart of the material. In that circumstance, we also say that the resulting displacement field should be continuous. And that's necessary for, again, the body to remain compatible or continuous after deformation. Now, we can verify that that's the case by actually figuring out what is the displacement field. But oftentimes it's a little bit difficult to do, which is why we had this compatibility equation, which really just was an expression that pertained only to the strain field itself. But it really is limited in certain applications. It's limited to scenarios where, the strains are, or the strain field itself is continuous. Now, it is possible to have a discontinuous strain field, but still have a continuous displacement field. So if you were to look at this resulting strain distribution, and you said, well, the strain field is not continuous, therefore, we don't have a compatible deformation field. That's not necessarily true. It is still possible to have discontinuous strains, but to have a compatible deformation field nonetheless. That happens in practice quite a lot, actually. At any material interfaces where there might be a sudden change in material properties or other things like that, you can have discontinuous strain fields occur. So we can't necessarily rule this out. It might still be compatible. And we've certainly verified that within each of these domains, we've satisfied compatibility. So, there is a compatible deformation occurring due to this strain field in this upper part, as well as in this lower part, and each of those subdomains result in compatible deformations. The thing we really don't know is what's happening along this interface, along this line y=1. And that's the thing that we really need to come back and verify and double check. Well, maybe we don't necessarily need to know what is the displacement field or, the actual deformation of this whole region. All we really need to know is if I were to take this strain field and this strain field and come up with some guess of what the resulting displacement field should look like along this interface, I need to verify, does the displacement field that would give rise to this strain field match with the displacement field that would come from this strain field? So that's really the thing that you would have to go back and verify. So we're almost all the way there, but we do still need to verify, okay, can we satisfy compatibility in this much broader sense? Not just the compatibility equation, that simple 1D equation in this two-dimensional sense. We need to actually go back to the original definition of compatibility and acknowledge that it's a constraint on the continuity of the displacement field, not just satisfying this simple equation. Okay, so how do we do that? We have to come back to Muhammad's suggestion. We have to basically say, let's actually come up with the displacement field. So we got to integrate this thing. At the end of the day, we had to do it all along. So let's do that. Let's come up with the displacement fields in each one of these things, but isolating attention to just this line where y=1. Now I'll ask, what different components of the displacement field do we really need? Which components do we actually have to verify? There's two components. There's the x component of displacement and the y component of displacement along this interface. And we could get both of them. We could try doing that. But, which one do you think is more important? The y. Separation, basically. Yeah, that would be true. That would be true, but you'll see why maybe that's not necessarily necessary. Okay, so let's actually take a look at this. Let's suppose we tried to, basically come up with an expression for the y displacement, just for the sake of argument. How do we come up with the y displacement? Given this expression for, let's say, y strain. Integral with respect to y, you say? Wish I had another pen. Oh, well. Anyway, so yeah, let's try this. Let's suppose really epsilon yy. Integral of epsilon yy with respect to y should give me displacement in the y direction. But is that all? Is that all? Remember, we had some homework problems that talked about this. If you're trying to obtain an expression, some generic expression for the displacement field, and I'm not telling you or giving you any other constraints to impose on what this displacement field looks like, should there be another term here? Yeah, there might be some kind of arbitrary function. In this case, it would vary with position x. Okay. And then same thing, we could determine, if this was, let's say, the displacement in the y direction, we could take this integral. We could do it for the top half of this domain. We could do it for the bottom half. And we could evaluate these resulting expressions at the particular value of y equals 1 and then compare them, basically. That would be one way that you do this. So we could do this basically for, on the plus half, I guess you could call it the top half, or the bottom half, the negative half. Just kind of introducing some notation here. And maybe there would also be some arbitrary function that might look different on the top or bottom half, which varies as a function of x. All right, and then the question is, can we verify that this resulting expression, let's say u on the top half evaluated at y equals 1, is that equal to u on the bottom half at y equals 1? And we could verify, when do we actually satisfy this condition? But I want to point something out. We don't really know what this function is. In general, it could be some arbitrary function, and it's different on the top and bottom halves. And we can add it to both of these expressions. And if we evaluate both of these expressions at the constant value of y equals 1, then each of these resulting expressions will be expressed purely in terms of x. So some function of x on the left-hand side has to be equal to some function of x on the right-hand side. And that would be fine. We could basically compare what is this resulting term on the left and right-hand sides, a function of x. And, basically, again, plugging in y equals 1 means there's no dependence on y in this particular comparison that we're making. But it will involve x. So that's the thing. That's the thing that we can't necessarily hammer down what this expression is. And in fact, if I give you nothing to specifically tell you what this function looks like, some boundary conditions or something like that, then really we could choose any possible function here such that we will always satisfy this condition. So it turns out, if we're trying to make this comparison by just looking at the y displacement without any additional information, there's no way to actually verify, well, is this going to result in a compatible y displacement field? It depends. It depends on our boundary conditions, how we define the boundary conditions, and whether or not it results in some kind of value for this extra term f on the plus and bottom sides. And maybe it will, maybe it won't, but we can't say definitively. We could pick it such that we do always satisfy it. Yeah.
So is it because in this case, since you're defining the barrier between the two top half equations along the y-axis at the value y equals 1, that isn't possible? Let's say you switched it to the x-axis, then in this case, this would be possible?
I think in some sense, yes. And I think it might be that one way to look at it is exactly how you said. If we instead maybe defined this barrier, I guess, yeah, basically a vertical barrier. So looking at x equals 1 and then dividing it into these two halves, we would be more concerned with what's the tangential displacement relative to that interface? In the spirit of that idea, really that means in this particular context, if we have y equals 1, it's not so much the normal displacement we need to verify, but rather the tangential displacement. So almost like we need to verify, is there something that kind of indicates whether or not it's even possible for this strain field to exist by looking at what's the relative tangential displacement along this interface at y equals 1. So to do that, we have to look at not the y displacement field, but in this case, the x displacement field. It looks almost the same, so we'll change only a few things. All right, so if we're looking at the x displacement field, the tangential displacement field at this interface, really, it's the same thing, except we're integrating xx displacement, or xx strain rather, with respect to x, and we should get then also some arbitrary function of y. Okay, simple enough. Then we need to verify, is this expression for the displacement in the x direction evaluated at y equals 1 the same along that interface for all possible values of x? So at any location along this length, is this expression still satisfied? So we need to verify u plus of x evaluated at y equals 1. Is that equal to u minus x at y equals 1? All right, so if we plug in this particular value of y equals 1 into this expression, what we'll get is basically evaluating this function on the plus and minus halves of this domain at this specific value of 1. So it's going to be a constant value. So we could call it f on plus or minus sides of this expression, but at the particular value of y equals 1, it's kind of like we just have some arbitrary constant that might differ on the plus or minus halves of this domain. We still don't know what this constant is. We could choose it arbitrarily such that we do satisfy the conditions of compatibility or we don't. It depends on the boundary conditions. But importantly, in this particular scenario, now we have expressions for ux that we can directly compare and which vary as a function of x position. So really, because this now is just some random constant, we can still compare how does the resulting expression for ux vary as a function of x and consider that kind of linear variation or quadratic variation with respect to x in both of these terms and compare those terms, forgetting about the extra constant terms that might appear. And we can say, does that variation in x for each of these two terms basically lead to incompatibility? So for this particular problem, it means we can forget about having to deal with this extra constant of integration and really just look at the integrand term. So looking at epsilon xx integrated with respect to x in both of these cases. And then we can compare. Do those terms, forgetting about the extra constant of integration, do those terms match when we set y equal to 1? So I'll ask, what's the integral of epsilon xx with respect to x on the top half? Minus c, there should be y cubed sticks around times x. If we evaluate it at y equals 1, then this term just goes to 1. And on the bottom half, cxy squared, which if y equals 1, just goes away. So really what we're comparing is minus cx and plus cx. Those terms obviously have the same magnitude, but opposite sign, which basically tells us that there's no possible way for this interface to actually result in a compatible displacement field because these terms are totally different from each other. And because of that, we rationalize exactly by the procedure that I just mentioned. Just integrate the epsilon xx strain to get some generic expression for ux on the top and bottom halves. Compare these terms when y is set equal to 1, and you'll find that indeed we don't satisfy this condition. So compatibility is not satisfied. And again, we satisfied compatibility everywhere interior to each of these top and bottom halves of the domain. We just didn't satisfy it along this interface. Okay, so a bit of a curveball, but that's kind of the spirit of this. It's really to get you thinking, and there's still some pedagogy to be had going into this exam, just so that you're really solidifying your understanding of these concepts, and that compatibility is really more than just here's an equation, let's apply it. It's an implication that the displacement field has to be continuous. All right, so with that, let's move on to problem number 2. So this one's kind of fun, and it's very practical, actually. I give you this hollow cylinder, and I'll just paraphrase what's written here because it's very much just, providing you with some extra color and justification of why this problem is useful in practice. But the idea is this: let's take some long hollow cylinder and treat it as being subject to plane strain conditions. So even though it's a long hollow cylinder, we can use our assumptions of plane strain to just treat this as an equivalent two-dimensional problem. So in cross-section, we might be looking at something that looks like this. Some sort of annulus that has an inner diameter di, outer diameter do, and has some inner pressure. So internal to this cylinder, there's some pressure P being applied to the inside surface that always acts strictly normal to that inner surface. And on the exterior surface, we're not applying any pressure. So it's just, traction free, basically no stress on the exterior of the cylinder. So a pressure vessel, a long hollow pressure vessel. Now, in some cases, you might want to solve this original problem. But it turns out for a lot of these problems that involve axis symmetry, which is to say that really, if you were to look at any kind of circular sector or arc of this problem, it all looks the same, regardless of whether I'm looking at this little slice or this little slice of the pie. It looks the same, maybe differing by some kind of angle of rotation in terms of how it's oriented. But, with respect to the angular coordinate theta, thinking of things in terms of cylindrical polar coordinates, it looks the same. And we could consider reducing this problem even further, going from what was originally this three-dimensional problem using plane strain assumptions to go down to this two-dimensional problem. And we can reduce it even further to what is almost like a one-dimensional problem using this assumption of axis symmetry. And what I ask you to do in this problem is not to solve this specific boundary value problem, but rather to just set up the problem, define the boundary conditions, not of this original kind of axisymmetric kind of looking plane strain problem, but rather give me the boundary conditions that would still give me an equivalent solution to this problem, but just considering a small wedge of this circular arc. So that's really the question, and it's intended to really hit at are you aware of and able to define a well-defined or well-posed boundary value problem? I'm not asking you to solve it. It really counts for a lot just to be able to define the problem and set it up in a well-posed fashion. So you should expect to see a problem very similar to this on the exam that basically is asking you to do something like this. Don't solve the problem. Tell me what the boundary conditions are. That's all that I'm asking you to do here. So how do we do that? How do we actually define boundary conditions? And first of all, what are boundary conditions? Remind me. Traction boundary conditions being one of them, and displacement boundary conditions. So really, when I say boundary conditions, I mean two things. I mean, what are basically at all points along this boundary of this domain. And for simplicity, let's not consider the front or back faces of this, slice. Let's just consider, these edges as viewed in a two-dimensional context. So the inner circular arc, the outer circular arc, and these two kind of radial lines that segment this circular arc. Along that boundary, we need to define boundary conditions. And remember, we have to define boundary conditions everywhere along the boundary in order to come up with a well-posed boundary value problem. If you just say, well, the normal pressure on the inside of the cylinder is P, and then there's no pressure on the outside, and we don't say anything about what's happening along these kind of like linear edges, and you leave it at that, I would say you haven't set up a well-posed boundary value problem. You need to be specific. You need to define boundary conditions everywhere. So that's really what I'm asking you to do, to recognize how do you set up boundary value problems, and to also exercise your intuition to figure out really what should these boundary conditions look like. Should they be traction boundary conditions? Should they be displacement boundary conditions? Or should they be maybe some combination of the two? Such that I get, again, a problem that gives me a solution that should be equivalent to what I would get if I solved the original problem. Okay, so let's start with the easy one. We're going to have to use cylindrical polar coordinates. That's a little unfortunate, but it's not so bad in this case because, it's basically just a pure cylinder. So tell me, let's go segment by segment and define the boundary conditions for this problem. First of all, let's make sure that we remember definitions for traction. What is the definition of traction on a surface? Yeah, it's a force per unit area, and it's related to particular components of the stress tensor, depending on what is the normal direction relative to a given surface of interest. So if I'm looking at, let's say, some kind of circular arc on the surface, maybe it has some kind of normal direction that looks like this. And if I said I wanted to define what's the traction vector on this surface, how is it related to the stress components acting on this kind of block of material? Well, it may be worth kind of drawing out exactly what do the stresses look like on some chunk of material, kind of to answer your question. In a cylindrical polar coordinate frame, what do the different components of stress look like? Well, there's certainly, if we're defining a coordinate frame that maybe involves a radial coordinate and an angular coordinate, kind of like that. So any basically direction along this radial direction is kind of an R direction, and anything tangential or kind of circumferential is a theta direction. So to make room for the actual representation of the stress components, it might look something like this. We might have normal components of stress acting on the surfaces of this kind of small circular arc that look kind of like, maybe there's a sigma RR component of stress, which looks kind of like this. And there might also be a sigma theta theta component of stress. And you'll have to forgive the fact that technically speaking, it's a curved segment. So really these might look like they're pointing in different directions, but we have to isolate our attention to smaller and smaller arcs. So as this thing kind of shrinks to zero. We also have shear components. So let's say if theta is this direction, really the shear component of stress acting on a face whose normal is directed in the R direction, but which acts in the positive theta direction would look like this. So we'd have basically a sigma R theta component of shear traction that acts in this direction. And it would have to be balanced by basically an equivalent value here. And then by similar arguments, we can rationalize that really it's the same component of shear stress that acts on all of these four different faces. So the shear stress is the same on all four faces, and we have normal components of radial stress, or stress in the radial direction, and stress in the circumferential direction. You could also think of this as hoop stress. All right. So assuming that we have these components of stress defined on this, segment, we can now set about trying to define boundary conditions that set constraints on particular values of these stress components, depending on which surface we're looking at. So if we're looking at, let's say, points along this exterior surface, whose normal is basically aligned with the radial direction of our cylindrical polar coordinate frame, as is the case with, like, let's say, this outer circular arc. On this surface, with normal that points in the radial direction, I want to know what are the constraints that I would impose on the different components of stress along that boundary. So which components of stress should we look at for that particular exterior curved surface? Well, amongst these different components of stress shown on this diagram, which ones are actually exposed on this exterior circular arc? Theta r and sigma r theta. So basically, if we're trying to impose boundary conditions, traction boundary conditions, on this exterior surface, the only components of traction that we could constrain are basically the RR component of traction and the R theta component of stress, technically. So in this case, if I'm saying that on this exterior circular arc, I'm not imposing any kind of stresses, no tractions are imposed there, what does that say about how these resulting components of stress should appear? Yeah, basically, if I'm saying, at least visually, it doesn't look like I'm imposing any displacement boundary conditions. So the only thing I'm imposing here is traction boundary conditions. And traction boundary conditions can be zero stress conditions. In this particular case, on that exterior circular arc, it'll basically say that the radial and tangential shear components of traction on this exterior arc are equal to zero, both of them. So we're not applying any kind of shear force. We're not applying any kind of radial force. All right, so sigma RR and sigma R theta have to be equal to zero along this arc. That's our first set of boundary conditions, traction boundary conditions on this exterior segment. What about this interior segment? Kind of applying similar concepts. Now we're looking more at this particular segment. Yeah, so shear, we can say by similar arguments, is zero. It doesn't look like we're constraining displacements. It doesn't look like we're applying any kind of shear traction on this interior surface. So yes, sigma r theta has to be zero on this inner surface. What about this pressure? What do we do about that? So sigma RR is the thing that we're constraining. And really, it should be proportional to this pressure load that we're imposing on that surface, the inner surface. But we have to be kind of careful here, because the sign convention for stresses, at least in this cylindrical polar coordinate frame, indicate that a positive value of sigma RR is actually pointing inward. If we're looking at a chunk of surface area whose normal is pointing not in the outward radial direction, but now in the inward radial direction. Basically, what that means is this arrow basically corresponds to the positive value of sigma RR. So if sigma RR is positive, it's kind of like we have a tensile stress that's kind of like causing this whole thing to expand. But you'll notice the P that we're applying on this interior surface, it's compressive. It's pressing into the surface. So what does that mean if we were going to try to relate sigma RR to this applied pressure load? Equal but opposite. Yeah, given the sign convention we've chosen for our stresses and our chosen coordinate frame, and assuming that P is this outward radial pressure, we kind of have to say sigma RR is really just equal to minus P. All right, so if P is indeed oriented in the direction we've shown, then really it should result in kind of a compressive stress right at that interface. So that's our first set of boundary conditions. All right. And you might write it something like this. You might write it as basically sigma RR and sigma R theta on this inner surface have to be equal to P and 0, where I'm kind of, instead of putting the negative sign on the P, I'm actually shifting it over onto the left-hand side of this expression, but it really gives you the same result in any case. And then on this exterior segment, we're basically saying that the RR and R theta components of stress are equal to 0. You could express that equivalently in terms of the components of traction, which, if you remember the relationship between stress components and traction components, it was obtained through that kind of Cauchy stress theorem. So really, the components of traction are given by this relationship. Assuming you have some kind of normal direction n, and you have some components of stress defined in whatever coordinate system that you've chosen, then the resulting components of traction, a vector, are obtained by this matrix vector multiplication. And you can use this just to do a sanity check. Really, what this means is that if n is pointed outwards, if n has components 1 in the radial direction and 0 in the tangential direction, then really we're looking at components of stress on this outward face. But if n points inward, so -1 in the radial direction and 0 in the tangential direction, then we get basically negative values for these components, giving us what the traction should be. So minus quantity for the inward normal multiplied by these stress components gives us apparent negative values for these tractions. That's precisely why we have these minus signs included here. If you were to go through establishing these relationships using Cauchy's stress theorem. Okay, now the harder one. What about these interfaces? You say displacement boundary conditions. Any other takers? Pure displacement boundary conditions? I mean, I think I partially agree. I partially agree that really what we want to have happen is that if, let's say, we have this cylinder, well, in practice, what do you think is going to happen to this cylinder if we impose an internal pressure load? Just, conceive of it in your mind and then describe visually what would happen. Yeah, it would expand. The whole thing would expand out in the radial direction. So a point that was originally here is going to deform or displace purely in the radial direction. It really shouldn't exhibit any kind of, displacement along the circumferential direction. That's characteristic of a lot of these axisymmetric problems, in which if you were to, let's say, I don't know, identify some subset of the domain that exhibits these symmetry planes. And a symmetry plane is really any kind of plane that you could cut through this, piece of the domain. And across this symmetry plane, we really expect the solution to kind of look the same or be reflected across that plane. So if we have a symmetry plane that looks kind of like this, and if we said the solution on either side of that symmetry plane should look the same, does it make sense then to have, let's say, a circumferential component of displacement such that maybe along this half of the body across this symmetry plane, if this point wanted to displace in the circumferential direction, but on this opposite side, if the displacement wanted to just, basically do the same thing in a reflected kind of fashion, then it would kind of look like across the symmetry plane, you're violating conditions of compatibility. Same thing, if across the symmetry plane points wanted to pull away from this interface, and if we're assuming that really it has to be symmetric, then it would apply that there's some kind of fracture that's opening in this thing. So to satisfy compatibility across the symmetry plane, what we really require is that we're actually specifying that the displacement normal to the symmetry plane has to be constrained. And in particular, it basically has to indicate that there is no displacement normal to the symmetry plane. So in this particular case, the normal to this cut line has a normal that points in the circumferential direction.
And hence, the displacement normal to this surface, the displacement in the circumferential direction, has to be equal to 0. That's a condition of symmetry, arguably also a condition of compatibility. So anytime we introduce a symmetry plane, we have to introduce this additional constraint on normal displacement across the plane being equal to 0. That's a good thing to commit to memory. You might want to remember that because you might need to apply that during the midterm exam. All right, but how does that manifest in terms of the boundary conditions? That's certainly something consistent with what you said. There are displacement boundary conditions. Indeed, if we have this symmetry plane, then we're saying normal displacement along that interface has to be equal to 0. But what about the tangential displacement, or the displacement now in the radial direction? Is that constrained? No. It would make it look a little funny if it were constrained, because then it would kind of be like you're fixing these entirely, and then this thing might like bubble out, which is really not what it would have to look like if we're trying to solve the original axisymmetric problem, right? Really, we want points along this kind of interface to just slide freely, unconstrained, such that they can displace outward radially in the same fashion as any other points that might lie interior to this circular arc. So for that to happen, we really need to say that there's no displacement boundary conditions or constraints imposed on radial displacement. And if we're not specifying a displacement boundary condition there, we need to specify something else. We can't just say, just omit what that radial, displacement boundary condition is. Just say there isn't any displacement boundary condition, we're done. You have to be specific. At every point on the boundary, you have to specify either displacement or traction. So if we're not specifying radial displacement, we have to specify the component of traction that acts in the radial direction on that surface. In particular, we have to specify this component of shear traction along this surface. But of course, if there's nothing constraining these points from sliding along the symmetry plane, it's equivalent to saying that there is no shear traction on that interface that would otherwise prevent these points from sliding outward. So in some sense, we now have sort of a mixed collection of boundary conditions defined on these symmetry planes. We have both that the normal displacement or displacement in the circumferential direction on both of these planes has to be equal to 0. And we also have that the shear components of traction acting on these faces are also equal to 0 to allow the points to slide freely along those interfaces. So in all, it might look something like this. And if you'd like to visualize it, as I do, you might think of things sort of in this representation of almost thinking of these symmetry planes as being, replaceable with these roller constraints. So there's no constraint on, the actual radial movement, but there is a constraint on tangential movement. So if you look at these symmetry planes, you could equally just replace them with a collection of these rollers. Rollers that could still sustain some kind of tensile force, so they're magic rollers, but nonetheless, visually, that's kind of how you would rationalize it. So that's the boundary condition problem. Good to know all these different things, how to define boundary conditions in both Cartesian and cylindrical polar coordinate frames, bearing in mind how do we actually impose constraints on different components of stress, different components of displacement, and so forth. And again, there will be a very similar problem on the midterm. So, maybe study this if you feel like you need to reaffirm certain relationships in your mind, relationships between traction and so forth. All right, problem number 3, which is really a 3-part problem. And unfortunately, we've kind of only got 15 minutes left or so. So I'm only going to be able to give you kind of a flavor of the approach to solving this problem, but I invite you and I encourage you to go back, maybe practice these, work them through by hand. Really, I just want to give you the tools to know how to approach them. All right, so this is sort of an interesting one. It has practical applications. Suppose we had some, you could call it a 3-point beam bending experimental test. Something that you actually probably have, maybe some of you have even gone into the laboratory and run these specific tests before. But in general, they kind of look like you have some prismatic specimen that looks kind of like this with various dimensions as shown here. And it's supported by, let's say, some steel cylinders at its base, and also loaded by some kind of cylinder such that I'm applying a load 2p on the top, and then the resulting reaction forces are equal in magnitude of value p below each cylinder. And in this particular part 1 of this problem, what I'm asking you to do is figure out, given a particular value of p, let's just make it easy, say p equals 1 kilonewton, so a unit load, determine what's the maximum contact pressure that would occur between this top cylinder and the specimen at this point A. Now, if I were to ask you this, I give you a hint here. This hint will not be present in the exam. So you might want to copy this down. You might want to print out a version of this kind of thing because a very similar problem will appear. You'll need to kind of have this on hand. So do make note of this. Do plan to bring this kind of suggested hint and the resulting equation that is given with you to the exam. But in any case, if I'm asking you to determine what's the maximum contact pressure between these two interfaces, how would I go about doing that? And what principle would I apply? Yeah, say again? We would basically have to do, we would have to apply some of the concepts we covered late in chapter 3. Remember, what was one of the last subjects we covered in chapter 3? Yeah. So we applied this Hertzian contact idealization to come up with the distribution of pressure that results between contacting interfaces. We covered a couple of different instances of sphere-on-sphere contact. And in that situation, the resulting contact area was a circle. So between two spheres that come into contact, the contact area is circular, and we can determine what's the maximum contact pressure between these two contacting spheres as basically the point at which the bubble of contact stress that manifests over this patch or circular patch of area, when does it achieve a maximum? In the case of, let's say, a cylinder on top of this square block, neither of these are clearly, these are not these are not spheres. They're not even cylinder on cylinder, like we had kind of in that idealized problem when we were doing the homework. Remember when we did that problem involving like a wheel on top of a railroad rail? We idealized that scenario as basically a cylinder on top of another cylinder. So we could apply that general contact between two ellipsoids and come up with an answer. Now it's a little bit different. And the resulting contact area is not going to be a circle. It's not even going to be an ellipse. It's actually going to be kind of this rectangular area. Almost as though you could idealize this as being two cylinders on top of each other, where the top cylinder has this characteristic radius r, and the bottom cylinder, as kind of idealized through this, rectangular specimen, has a radius that is effectively infinite. So if you like, anytime you have a flat interface, or at least if one of the objects that's in contact with some kind of circular object looks like it has a flat, basically a flat surface, you can still treat it as a circular surface, just with an infinite radius. It's kind of a hack. It's a bit of a trick, but really that's the trick that you would apply in applying this kind of formula. I give you a hint that the contact pressure between two cylinders that otherwise have relatively equal length is given through this rather direct formula. So really all that this problem is asking you to do is to apply your understanding of that observation. That if I have a flat surface in contact with this cylindrical surface, I can still use the same formula as cylinder on cylinder contact, but just plug in R equals infinity for this kind of lower object. So, and that's really all that I'm asking you to do here. It shouldn't really be any more challenging than that. And you can go about doing it by, again, plugging in exactly these different conditions into the formula. I'll, again, encourage you to go through this, work it through by hand, and make sure that the resulting values you get here are consistent with what's shown here. But it's not particularly illustrative to go through all the hand computations to demonstrate this. So really just apply the formula, recognize that it's, just a special case. All right. So part 2 asks you to use your result from part 1. In the actual exam, if I have this kind of multi-part question that I'm putting to you, I'm not going to ask you to have gotten everything right on part 1. Instead, I'm probably just going to give you something that will help you basically do these problems almost independently. So you shouldn't have to have solved part 1 or even gotten a correct answer to be able to go on and then solve part 2. You should be able to just solve each part independently in the real exam. In this exam, though, in the practice one, it's a little bit more challenging. I'm asking you to take that maximum contact pressure P naught that acts at this point, and to then determine what is the total state of stress and strain at both points A on this front face of the specimen directly below the application of this load, and point B, kind of also on the front face of the specimen directly above this point of application near one of the supports. Now, let's first go about asking, how would you, given that you know what the vertical component of stress is, and I also say just ignore any components of external shear traction. Suppose that this top cylinder and this bottom cylinder, they don't exert any kind of shear force through contact with the beam. So ignore shear tractions. What would the resulting stresses look like at each of these 2 points, A and B? Just kind of visually. All right. I'm telling you at least one of them, right? If, let's say, we look at point A, let's just zoom in. And I said there's some contact pressure. And let's actually represent it as a cube, let's say. There's some kind of contact pressure that's acting at point A. All right. Same thing with point B. If this is the case, if you're able to determine what is this contact pressure, and you can determine what's the contact pressure at point B just by applying the same formula that was given in part 1 of this problem. Assuming you can characterize both of these values at A and B, what is then the resulting stress distribution in each of these 2 points? Do we have enough information?
Pressure opposite on B, like
Yeah, basically. So if we're looking at what is the stress distribution in some cube generally, the different possible components of stress might involve, normal stresses on each of the different faces and shear stresses. Really, what I'm asking you to do in this problem, if I'm asking you to determine the full state of stress, all of its components on some chunk of material at A or B, and I give you maybe some conditions on what the external stresses are, I'm asking you to determine, well, what should these resulting stress components look like? You have to apply some notion of understanding of the boundary conditions for this problem, and also understanding what other stress components are missing or not prescribed through the boundary conditions alone. This actually goes all the way back to one of the early homeworks that we did. It might have even been the very first homework problem or set of problems we did, where there was some kind of beam. And there was some, distribution of tractions acting on the top face of the beam. You remember this problem? And the problem asks you, what is the stress acting at these two different points, the top and bottom faces? So in some respects, we're kind of doing something similar in this context. But now it's a little bit more challenging. So you're right. I want to point out that indeed, if we have this vertical pressure, it should be balanced. And really what this means is, anytime you have one of these blocks of stress, if I'm trying to determine, let's say, different components of stress acting in different directions, I can use the fact that I know that really the stress that's acting on the top of this block is P0, the contact pressure, which basically has to be equal to sigma YY. It's a compressive value, so really I should say that this is minus P0 at A. And then that way I actually hammer down what this specific component of stress should be acting at point A. But that's just one component of stress. In general, I have to define all these other components of stress. Yeah.
There also be compression at A too.
Compression at
Like,
A.
sorry, I mean like there would be compression.
Yes. So sigma XX, that's the thing. How do we characterize sigma XX, sigma ZZ, all the other shear components of traction or stress defined at this particular block point? To determine all these things, we can use boundary conditions, kind of in the same way that we determined what's the vertical component of stress acting on the top of this block. We said that there's a contact pressure there. It's compressive, it's pushing down on the top of the block. But remember, boundary conditions, what you see is just as important as what you don't see. So if I look at whether or not there are any shear forces acting on the top face of this block, I say that you can neglect any kind of shear forces acting between the cylinder and the specimen, which basically means that any components of shear traction that would act on the top face of this block, you can just say they're zero. So really these components of traction, shear traction or shear stress, in this case, sigma y in the x direction, sigma y in the z direction are both equal to zero. Through symmetry arguments, you can also then rationalize that the component of sigma xy stress on the x face acting in the y direction is also equal to zero. Because we say that sigma xy is also equal to sigma yx through basically moment equilibrium. So we can hammer down those different components of traction. We can also look at what's happening on the front face of this kind of specimen. At point A, this exposed front face has no tractions applied to it. There's no external pressure. There's no shear forces acting on that front face, which also implies that these components of stress, sigma ZZ, equals zero. And same thing, these components of shear stress, sigma Z in the y direction equals zero, and sigma Z in the x direction equals zero. So basically all of these different components of stress, at least on the front face and on the top face, except for the vertical stress, we can directly specify just by knowing what the boundary conditions are on this exterior point of the body. So that's the special thing. Anytime you're looking at this sort of edge of the domain, we can fully specify all these different components of stress. But the only thing that we can't specify is this XX component of stress. This is the thing that we just don't have information about. Our boundary conditions are just incapable of prescribing or telling us anything about it. So really, there's almost nothing that we can do, at least just by looking at the boundary conditions. But we can apply classical principles from mechanics to go back and figure out how do I actually determine what's the internal bending stress distribution in this beam. Remember if this was idealized as a simple beam and you were back in your strength of materials class, applying your regular principles of mechanics to figure out what's the assumed linear distribution of stress, bending stress, in this particular cross-section of the beam, how would you figure it out? I heard it. Yes. My over I. Say it proudly. Yes. My over I. That's the assumed linear bending distribution. So sigma xx, if I have some beam, running out of juice, but if I have some beam, what's the resulting bending moment distribution going to look like for this beam? Simply supported with a point load in the middle, right? Right. If I were to plot a bending moment diagram, it might look something like this. So M as a function of X might kind of linearly ramp up to the point of application of the load and then ramp down. And the actual maximum value of this moment, right in the middle, below that kind of point of application of the load. Well, you can figure out in a few different ways. You can, go about solving this simple kind of like beam equilibrium problem. You can solve for what's the resulting shear and bending moment diagrams. But what you'll find is that this should have a value of PL over 2, something like that. I encourage you to kind of go back, review this, maybe kind of refresh your memory on like shear and bending moment diagrams. It still applies here. But the linear variation of XX stress, assuming this sort of classical beam bending stress distribution that varies linearly with height y above the neutral axis, is simply my over I, right? So assuming that I have some value of m, which I can determine in terms of the applied loads p, in this case, it might actually have to be 2p because I'm applying a load of 2p in the middle. But I can apply this formula, come up with m, figure out what's the maximum value of y, and divide by the moment of inertia, I, really the second moment of area. And I can use that to then determine what's sigma xx. Now, we've run out of time, unfortunately, but I encourage you to still go through some of these problems, continue to work through them. If you have questions, I'd invite you to maybe visit me in office hours tomorrow. Get some practice. The slides also contain the answers to a lot of these questions as we go through. But in any case, if you have questions or other kind of concerns in advance of the exam, feel free to come chat with me. Otherwise, I'll see you then. Yeah. It should be shorter than this. It shouldn't be quite this long. Yeah. Yeah. I think I've already actually uploaded these set of slides, so it should be, you can find it on Canvas, but yeah. All right, I'll double check.